All right, 12.6 is on statistical measures. Ooh, stats. All right, so random sample is a sample in which all the members of the population and all groups of members of a given size have equal chance of being in the sample. Very confusing. So you can think of the different things that we've done, random samples, like rolling dice, flipping a coin, things like that. Data can be divided into two types. You can have quantitative data. So quantity, what does that mean? Quantity? It's a number, it's like an amount. So it's numerical data, so think numbers. And you can have qualitative data. So this is data that is categorical in nature, such as liberal, moderate, conservative, blue eyes, brown eyes. This has nothing to do with numbers, right? All right, so then quantitative data, so that breaks into two different things. So that breaks into discrete and continuous. So it's qualitative, it just is qualitative. We don't break it into any more. All right, so discrete data is data that has a minimum difference between the two values. So for instance, like the number of questions correct on an exam. Right, there's a minimum distance between those, meaning 1 point. One question could be different. Oops, no, why it's doing that. And continuous data is data that has no minimum difference between two values. So for example, the weight of an object. So why would that have no minimum difference for weight of an object? I don't know why I did that. It's the projector, it's not the machine. I don't know. All right, so why would a weight of an object have no minimum difference between? Like, yeah, you could say there's a pound between them.
But it could continue to be like infinitesimally smaller.
Yeah, it could be like half a pound, 0.1 pound, right? There's no like minimum difference between a weight, right? You could drink a little bit more water and get a little bit heavier. There's no minimum difference. Okay, so what are examples of discrete and continuous data? So let's think of some different examples. Sarah, any ideas? Sarah, Hendy? Come to you
like,
next, Matt. Think of some things.
Like when you weigh, like when you go to the grocery and weigh.
Yes, there's no minimum difference for weighing vegetables. Yep. Matt, think of anything? How about measurement? Yeah, how tall you are. Is that discrete or continuous? Kind of. If you're listing your height, maybe on a roster, right, on basketball rosters, you don't say, Kern is 5'10" and 0.34 of an inch. You don't say that. But really, people are. I mean, you really have fractions of an inch. So if you're like listing it on a roster, it'd be discrete, I guess. But if it's their actual heights, it's continuous. Okay, any ideas, Chris? No. They're all tired. First period. No one has any ideas on discrete or continuous. How about amount of rainfall? Discrete or continuous? Continuous, right? There could be just a little bit more. The weight of someone. You're stuck on this weight thing, Sarah. I don't know. Maybe how far you throw a shot put? Is that discrete or continuous? Continuous, right? It could be a little bit further than the last one. All right, so we have lots of different examples. All right, so number one, so it says identify the data as either qualitative or quantitative. If it's quantitative, then list if it's discrete or continuous. So the number of questions answered correctly on a true-false test. Qualitative, quantitative. Quantitative, it's a quantity, right? It's a number. Santiago, you confused? Okay, so it's a number. So since it's quantitative, is it discrete or continuous? Discrete, because there's an actual like minimum number between those. You could either have 5 questions right, 4 questions right? The difference is 1 question, something like that. So it's discrete. Okay, the weight of each animal in a zoo. Is it a number? Yeah, so it's quantitative. right? Discrete or continuous? Continuous, right? A person's blood type. Qualitative, right? That's not a number. All right, so frequency is the number of times a certain value occurs. So if we talk about like the true-false test, if I give you a 10 question true-false test, there's going to be several of you that are going to get 8 correct. You know, that would be the frequency. So if, let's say 5 of you got it 8 correct, the frequency would be 5. Okay, the relative frequency is the frequency divided by the total number of responses. So let's see, there's 5, 6, 5, 6, 7. So there's 16 of you. So the relative frequency would be 5 people had the choice 8 out of 16. So 5 out of 16 is the relative frequency. Make sense? Okay, so number 1, it says a class of 25 students took a math test. Of these, 4 earned A's, so their grade was A's. So that means that's the frequency. 4 had A's. 11 earned B's. 7 earned C's. 3 earned, this is an old notes, F. It's from my previous school. I must have copied it. That stood for no grade, because they wouldn't get credit. Doesn't make sense. So you would get 4, 11, 7, and 3, so that's 15, so 25. So 25 students in the class, right? So if we talk about the relative frequency, that would be 4 out of 25, 11 out of 25, 7 out of 25, 3 out of 25. Pretty straightforward, not bad. Okay, so since we're in the statistics section, we're going to make a bar graph. You guys have all probably done bar graphs, right? Yeah. Okay, so for our bar graph, you always have to label. So on the bottom, I'm going to label grade. And along the side, I'm going to label frequency. So I have different grades. I have A, B, C, and F. And we want to show how they're related to one another. So A, there were 4 people that had A's. So you can do marks along the side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 4 people got A's. $11 people got B's. 7 got C's. And 3 got F's. Okay, that would be a bar graph. But obviously this isn't the only way that you can come up with ways of representing your statistical data, right? What are other types of graphs you could possibly have? A what? A line graph. You can have a line graph. So do you guys know that one? So a line graph would be like going from one to the other to the next. This would be like a line graph. What else? What? Pie graph, right? I like pie. We've talked about that. Pie the number. Pie the dessert. Pie graph. Anything else? Okay, there's something that we're going to learn that's called a stem and leaf plot. Okay. You guys have seen those. We'll talk about that as well. All right, so common distribution shapes. So distribution is just like if I listed out all the data, you know, in this last example, we had kind of a lot towards the middle. You see how we have a lot in the middle, and then the ends are kind of lower. Okay, so that's a distribution. Okay, so uniform, all the data values have approximately the same frequency. So if we had an equal number of A, B's, C's, and F's, it would just be kind of flat across, right? All our rectangles would be the same height. Okay, so a uniform is going to look just like this. So it's just like straight across. Okay, symmetric, the right and left sides of the distribution have frequencies that are mirror images of each other. Okay, so this could look a couple different ways. It could look like the bell curve. Have you guys heard of the bell curve? We're going to talk about that in 12 points. 7. It could also, I mean, it doesn't have to be the bell curve, but it could just be symmetric. It's kind of hard to draw. So just the same on both sides. Okay, skewed right. This is really tricky for people. Skewed right, what do you guys think? So think of your bell curve. Which direction will like the little bump be? Will it be on the right side or the left side? The left side, because you read it already. Or you just knew? You what? You're quiet today. So the right side of the distribution has much lower frequencies than the left. Okay, so if you have a long tail, whoops, if I know my right and left, that would help. A long tail to the right, and then the bump is on the left. That would be skewed right. Weird, isn't it? I would think that's skewed left. All right, and then skewed left, the long tail is on the left, and then you have your bump. So maybe right tail left, tail right. I always got those confused. All right, so let's kind of think about these different things. So from the common distribution shapes, choose the best distribution for the data. So A, the ages of all people in an elementary school during a typical school day, including faculty and staff. Would that be uniform, symmetric, skewed right, skewed left?
How many faculty are employees?
Well, I mean, think about faculty here. We have a lot of teachers here, but do we have as many teachers as students? No. So their ages are going to be really small, right? I mean, if it's elementary school. So if we're going to have an elementary school, that means that most of them are going to be pretty young. So they're going to have a big block over here, maybe even kind of flat across right there from ages 5 to 12. Depends on if your elementary school has 5th grade, 6th grade. All right, and then all of a sudden it's going to drop down. And then you might have a little bit over there. I mean, you might have a little bump or something over there. But where's most of your data? Yeah, it's on the left, so it's skewed right. You could also think of it, you'd have to shift it over to the right in order to get it back to like a normal, like a middle distribution.
What if it was just like, in general, like the ages of the people in an elementary school? Like that could be.
Like just
anywhere.
students?
Yeah,
That would be more uniform. Does that make sense?
because like it's still like 5 to 12, like that's a lot of years, but like.
Yeah, but they're all, I mean, if you
But
talk
it's
about,
still, like,
if you do a bar graph, right, if you do a bar graph and you talk about all the 5-year-olds, it's pretty even with all the 6-year-olds, all the 7-year-olds. They're all pretty even.
So it would be uniform?
At university, I think that sometimes isn't the case, right? We've had graduating classes that are really small, and then the next year it's really big. So it just kind of depends on the year. All right, so B, the age of death, or at death for people in the United States. It's very morbid. So the age of death. What do you think? Yeah. So most people don't die until they're later on, right? I mean, there are people that are going to die sadly in like their 20s or when they're really little, but most people are going to be over here. Okay, so that's skewed left. The day of the week of all students' birthdays in a school where Sunday is 1, Monday is 2. So let's try that. So how many of you were born on a Sunday? Do you guys even know?
I'm not.
Okay, never mind. Maybe we'll look that up later. Let's see what day you were born. Have you ever heard the little rhyme? It would be symmetric, right? Or uniform, actually. Yeah. Uniform. Because they'd all be pretty much the same height, right? Straight across. Now, uniform is also kind of symmetric. So, kind of tricky. But symmetric usually has more like bumps and things on the sides. Okay, the IQ scores of all the men living in the United States. Symmetric, right? So what's it going to look like? Yeah, it's probably going to look like that bell curve. So there's going to be a lot of average people. And then some people on the right are geniuses, right? Super smart. And then some people on the left, not so much. So it's kind of in the middle as the average. All right, so an outlier is a data value that is far removed from the rest of the data, which usually indicates the value needs investigation. So an outlier would be something that's way out here. Okay, so if you're running tests, like one of my best friends runs tests for diabetes. She's trying to find a cure for diabetes. And her data had a lot of outliers. So she couldn't present her paper because she had so many different outliers. I mean, you have to investigate those, like the reasons why there's these outliers. Okay, so there's people that will mess up your data. All right, so number 1, it says a supermarket manager wants to know how long customers are waiting in the express lane. A random sample of 15 customers is taken according to wait time in minutes. Create a stem plot, so we haven't talked about that yet, of the data below and discuss its shape. So we have 3.1, 1.1, 3.1, 3.2. So most of them, I mean, the most is, what did we get to? 3.4, it looks like. That's a pretty good supermarket. All right, so here's our stem plot. I'll kind of show you what they look like. I have some over here. These are stem plots. This represents 85, 91, 99. Oh, I don't have another one there. Keep going. All right, so now we have decimal points. So that's kind of tricky with stem plots, but it's okay. It will work out. So we have 0, and I'll do point. I have 1 point, 2 point, 3 point, and that's all I need. And then we just fill in all the different data, and then we're going to put it in order as well. So you can kind of do it. I usually have to do it in 2 steps. So I do 2 stem plots. So I have 3.1, 1.1, 3.1. See how I'm writing that? It looks like 3.11, but it's representing 2 data points, 3.1 and 3.1. Does that make sense? Okay, then I have 3.2, 0.5, 3.2, 3.4, 2.8, 3.2, 3.4, 3.1, 2.3, 1.7, 2.1, 1.5. Okay. And see how they're not really in order? Usually we like them to be in order. So our stem plot would actually look like, you'd go through and you'd write the numbers in order. So you had 5 on top. You have 175, so you would rewrite that as 157. Two, we have 831, so we need 138. 3, we have 1, 1. We have another 1 at the end. We have 3 2s, 2, 2, 4, 4. And the reason we like for it to be in order is because a lot of times you'll have to find like the median. Remember the median is in the middle number. Could you do that here? This would be the first number, last number, next, next. See how you can kind of find the median? You can go through and find the number in the middle. Okay, so you can find the median that way. And you can also find the mode. In this case, there's 2 modes. Mode means most often. So what values were listed most often? 3.1 and 3.2, right? Okay, so what's the shape of this graph? If I made like a bar graph, what would the shape be? Yeah, skewed left. There'd be most of the distribution would be on the right, so it'd be skewed left. So the long tail on the left, and then more on the right. Okay, the mean. The mean is a measure of central tendency. Central tendency means like mean, median, and mode. Also known as the average. We denote this by x with a bar on top, kind of like we did with complement when we talked about the probability. And it's read x bar. You might also see, instead of x bar, later on in math, you'll see mu. So mu is a combination of m and u, which is helpful because it's mu. That's how you spell mu. So it looks like an M. It also kind of looks like a U. So let me draw it real big so you can see. Makes sense? Cover up this part. It looks like a U. Don't cover it up. Kind of looks like an M. Hence the mu. All right. So if I'm finding the mean, you guys have done this before, it's just the average. You just add up all your values and divide by the number that you have. So the way we write this out is we say x1 plus x2 plus x3 dot 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 plus xn divided by, how many numbers do I have in that list? N. So divided by n. Okay, median, a measure of central tendency, so a measure of some kind of center that's in the middle of the data set. So median means middle. And then if there's two that are in the middle, so if you have an even number of numbers, you take the average of the two. So you take the median of the two middle numbers, or the mean of the two middle numbers. All right, and then the mode is most often. You guys should be pretty familiar with these, are you? Heard this all before? Okay. So find the mean, median, and mode of these numbers. So you guys can try this. So mean, median, and mode. I'll walk around and help. All right, so you need to find the mean, the median, and the mode of all the numbers. So what do you guys get for the mean? 3.75. Did everybody get 3.75? So I don't have to do that. So the mean, so you can write x bar, or you can write mu, 3.75. The median, these don't have fun letters. Median was what? 4. And the mode? 4. Okay. Most of the time they should be pretty close to each other, but sometimes they're not. So, all right. So there can be several distributions that have the same central tendencies. So for instance, these 3 symmetric stem plots have the same center. So they have the same median and mode of 105. Okay, but notice how they're all 3 very different. So one has, kind of that bell-shaped curve, probably the first one. This one's kind of a skinny bell-shaped curve, so it probably goes up real high and then back down. All right, and then this one's just all over the place. This one you go up. I don't know, something like this. I mean, that's all over the place, right? So it kind of depends. Okay, so it says the data has a different spread in each stem plot. So therefore, it's important to consider variability. Okay, so how much it varies from the central tendency. This is the spread of the data set, so how far it goes out. The second plot has the largest variability because the numbers are very spread out. Okay, the third has the smallest because they're all kind of scrunched in that middle. And then there are 3 common ways to measure spread. You can use the standard deviation, range, and interquartile range. All right, have you ever heard any of these words? No. Has anybody heard standard deviation? Yeah. You've heard range, but you've heard it in a different way, right? Range is like all the y values of a function, right?
Oh, so this is right.
That's not the same thing. You what? Yep, that would be the range. Yep, good. All right, so deviation. So the difference of a data value xi and the mean. So you would write it as x bar minus xi. Oh, let me do xi first, actually. It's not going to matter anyway. Or if you like using the mu, you can write it like xi minus mu. Okay, positive and negative distances might cancel each other out. So this is the problem with this, because if you notice in the second stem plot that we have, there's a huge range of numbers, right? It's really big. It's really spread out. But if we do this xi minus x bar, like this could be a distance of 5 and this could be a distance of -5, and we add them together, they cancel each other out. So it's not telling us anything. It's kind of like they didn't have any distance at all if we add up all the different deviations. So what we end up doing is we square them. So why would it be nice to square these numbers? So why do we square? So if I had 5 and I had -5, I want to know how big it is when I add them all together. So if I square them, I'm going to get 25 for both, and then I add them together.
They don't disappear.
They don't disappear. It gives you a bigger number, right? So if you take those big numbers and you square them, it's making it even larger. And then you don't have to worry about your sign. You're just adding up all positive numbers. Okay, so if it had small numbers then all those numbers before you squared them were really small. Okay, if they were big numbers originally, when you square them, they're even bigger. Okay, so that's why we square them. Okay, So we square each deviation. Then we take the average of all those once we add. So we add them together and divide by the number of deviations we had. This is called the variance. All right, your calculators are very handy and they do variance for you. I'm going to give you ones that you can do by hand. Don't you love it? Okay, so let's try this next one. Okay, so I have all the steps written out. So the first thing we need to do is find the mean of the data. So for number one, we're going to find the mean. So x bar, or you call it mu if you want. So we know how to do that. We're just going to add 81, 87, 91, 92. Do you guys see where I'm getting these numbers? 94, so like 81, 87, 91, 92, and so on. So 94, 96, 97, 101, 104. Add them all together, divide by the number that we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. Anybody there yet? You got what? 93.6 repeating. Okay, so go ahead and get that number in your calculator. So 93.6 repeating. You could do 93 plus parentheses 2/3 if you want.
So when you have like the 7 and the 11, do they just not count?
Yep, so there were no data values for those. Yep. If you had a 0 there, what would you put?
70.
70 and 110, right? Okay. It's going to be helpful to you if you store this number. So you can store the number, or you can keep using answer, right? As long as it's the last answer you had. But just in case you mess up and you lose, like you start typing in all this data and then you mess up somewhere, I'd probably store it just in case. Okay, so we're going to store. Do you guys remember how to do that? So hit STO, S-T-O, and then alpha A. Or you could call it M for mean. That would be good too. So whatever. Then hit enter. And then that number should come back up. Like it's showing you it's now stored. Okay, because what we need to do is we need to find the deviation for each data point. So I'm going to write store as A. Okay, here's what we need to do now. We're going to need to do 81 minus that A value plus 87 minus the A value plus 91 minus the A value plus ... So we need to find the standard deviation for each, we need to find the deviation for each data point. Oh, I forgot we need to square them. Dang it. Okay, so square them. And then we're going to add them all together. So let's do each individual thing. So we're going to square. So 87 minus A squared. 91 minus A squared. See how this is going to work? All right. It will be helpful if you do this all together, all in one line on your calculator. So then you have a nice, precise number, right? Okay, so we're going to do 81 minus A squared plus 87 minus A squared plus, and keep going. Takes you a little bit. Remember, you can always use insert and delete. You don't have to clear everything out if you make a mistake. Okay, so now I've added all those numbers together. So I added them all together, and then I take the average, so I'm going to take that number. So I got 392 when I added them all together and squared. And you're going to take 392 and you're going to divide by 9. We had 9 numbers. So I got 43.5 repeating. Once you average those numbers, the last thing to get the standard deviation, oh yeah, up here, see how it says the standard deviation is denoted by the Greek letter sigma? It looks like a little O with a line on top. Like a line to the far right, sigma. That's the lowercase sigma. Do you guys remember uppercase sigma? We just did that. Yeah, uppercase would look like that. So this is lowercase. They look nothing like each other. Okay, and then when you divide, so when you take the square root, 43.5 repeating. So just do square root of your answer. What do you get? 6.5997. Somewhere around there. So like 6.6 around there. That's your standard deviation. Okay, and standard deviations are going to be really helpful when we talk about data. I guess I need to let you guys go and break. All right, so if I have something about standard deviation on your test and you have to do it by hand, I will give you those steps. So you'll have those steps. So you think you could follow all of those and be fine? I think you'll be fine. All right, so quartiles. Quartile, this used to show up on the I-step. Do you guys remember the I-step? Did you guys
Yeah.
Yeah, so some of my students came to me and they were like, what's a quartile? And I was like, that was on your I-step test. So it's kind of weird. It's not hard, it's kind of obscure. So anyway, so these are the medians of the lower and upper halves of the data set. So you're going to divide your data into the lower half and upper half by putting them in order. And then you're going to find the medians of both of those things. All right, and it's going to divide your data into 4 separate sections, quartiles, right, like quarters. Okay, if there are an odd number of data values, do not include the median in either half, so don't include that middle number. Okay, the interquartile range is the difference between the first and second quartiles. So you'd find Q3 minus Q1, so I'll show you what I mean by that. It represents the middle 50% of the data. Okay, so number 1, so it says find the quartile range of the data set. So first we need to put everything in order, which is kind of annoying. So let's see, we have 2, so 2 2s, 2 3s, 1 4, 1 5, no, 2 5s, 6, 7, 2 8s, oh, 3 8s. See how the crossing out helps. 2 9s, and 12, 13, 14, 15. Okay, so let's count how many numbers we have on the list. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We have 18 numbers. So we're going to divide it into 9 numbers and 9 numbers. If there had been 19 numbers, you just leave that middle number out. So you don't include it in either one. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've now divided the numbers. Okay. Now we find the medians of the upper and lower halves. So we have 9 numbers. So I'm going to go over 4, 1, 2, 3, 4. The number in the middle is my median. That is Q1. Do you understand why it's called Q1?
Yes, because it's the median of the first.
So here's the first quartile. Yep. All right, so then Q3 is going to be 1, 2, 3, 4. So Q3 is right here. Because it represents the end of the third quartile. So your interquartile range is just the difference between these numbers. IQR ends up being Q3 minus Q1. So it's 9 minus 4, so your interquartile range is 5. Okay, this is another measurement of spread. So the bigger the number, the more spread apart your numbers are. Okay, that's the last thing, right? Yep. All right, any questions on statistics?
It's pretty good.
Yeah, it's not super hard. I think you guys can probably do this section. It's not bad.